Hi, thanks for joining me. Today I've got an interesting problem which was shortlisted for the 2019 IMO, and this is a number theory problem. We have a and b being natural numbers, so strictly positive integers. We want to prove that a squared plus the ceiling of 4a squared over b is not a square, so a square number. So if you've not seen the ceiling notation before, it simply means the smallest integer bigger than or equal to your input. So for example, if we have the ceiling of pi, because pi is 3.14 something, the smallest integer bigger than or equal to that is of course 4. The ceiling of say 7.2, that's just going to be 8 because 8 is the smallest integer bigger than or equal to 7.2. And the ceiling of say an integer, say 6, that's just going to be 6 because of course 6 is an integer and it's the smallest one which is bigger than or equal to 6. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to show that this guy here is never a square is by contradiction. So we're going to suppose for contradiction that this guy here equals a square, and then we'll arrive at a contradiction. So firstly, notice if this guy here was a square, it would have to be a square that's strictly bigger than a squared, because obviously this is a squared and this thing here is a positive, an integer which is bigger than or equal to 1. So a positive integer. So it would have to equal a plus k squared, where k is a positive integer, like so. And then of course, just expanding this bracket out, we're going to get a squared plus 2ak, whoopsie daisy, plus k squared, like so. Then what I'm going to do is just cancel the a squareds from both sides, and then kind of let, because we notice here we've got a 4a squared, which is the same as 2a all squared, and here we've got a 2a. So I'm going to introduce c, which is just going to be equal to 2a. So this thing here just becomes the ceiling of c squared over b, and that equals ck plus k squared, which of course is just k times c plus k, like so. Okay, so now we have this new equation, the ceiling of c squared over b equals k times c plus k, k times c plus k, and now I claim that there are no integer solutions to this guy here, and of course that will prove this guy here, and in fact we don't even need to go as far as to prove that there are no integer solutions to this guy here. We only need to prove that there are no integer solutions where c is an even integer. Okay, but what I'm going to do is prove that there are no integer solutions to this, and this will take care of our original problem. The way we're going to show that there are no integer solutions to this guy here is we're going to suppose that there are, and then find the one which has the smallest value of k. Okay, so suppose that there are, and then just choose one with the smallest value of k, and notice that that's well defined because here c, b, and k are strictly positive integers, so there's going to be one, or there may be a few, but with multiple, with the smallest value of k, because k of course is bounded below by 1. So we find the one with the smallest k, and then what I'm going to generate is another solution with a new k value which is strictly less than that smallest value of k, and kind of by infinite descent we arrive at our contradiction. Anyway, let me clean up the whiteboard and we'll move on to that. Okay, so I've written up the equation we just had, and I've also written up a little claim. I claim that c is strictly bigger than bk, and bk is strictly bigger than c minus k. Now let me prove this claim. So proof. Let's start with the first part of the inequality, c being bigger than bk. Well, notice that c squared over b is strictly bigger than the ceiling of c squared over b minus 1. Okay, so I claim this inequality here is true. Firstly, if c squared over b is an integer, then we can kind of get rid of the ceiling signs here, and we get c squared over b is strictly bigger than c squared over b minus 1, which is obviously true because minus 1 is strictly less than 0. Okay, what if c squared over b is not an integer? Well, let's say it's 3.2. So suppose c squared over b is 3.2, so not an integer. Then this guy here would be 4, then we get minus 1, so that equals 3, and of course 3 is less than 3.2, so this inequality here holds. So hopefully you can see why it holds in general. Okay, so we have this inequality here. Let's proceed, and notice that we have this guy here is exactly the same as that guy there, and that of course is just k times c plus k, so that's k squared plus ck, and then of course the minus 1 we have there. Now remember from before, k is a positive integer, so it's at least 1, so k squared minus 1 is going to be at least 0. Okay, because k squared, obviously, if k is a positive integer, that means it's at least 1, so k squared is at least 1, so k squared minus 1 will be at least 0. So this thing here is bigger than or equal to ck. So we get c squared over b is bigger than, strictly bigger than ck, and then of course just rearranging this, multiplying both sides by b, and then dividing both sides by c, we're going to get the first inequality. So c is bigger than bk, like so. So that proves shows the first part of our inequality. Let's move on to the second part, and we're going to start off with c minus k times c plus k, all divided by b. So the difference of two squares is just c squared minus k squared over b. And of course, remember k is a positive integer, so c squared minus k squared is going to be strictly less than just c squared over b. But we know c squared over b is going to be less than or equal to the ceiling of c squared over b, like so. Because remember, with the ceiling function, if it's an integer, you're keeping it the same, in which case we have equality. And if it's not an integer, you're bringing it up to the next smallest integer. So you get that guy there. And of course, this guy here is just k times c plus k, like so. So then just cancelling the c plus k on both sides and noticing we've got a strict inequality here. Rearranging, we get that bk is strictly bigger than c minus k, which is the second part of our inequality, and that proves our claim, like so. Cool, we've proved the claim. Let me clean up the whiteboard and we'll continue. Okay, so we just proved that c is bigger than bk is bigger than c minus k. Now if we just have a stare at that for a second, that means we can write c is bk plus some small term. So we can write c equals bk plus r, but r is a positive integer. It's going to be strictly positive because bk we know is strictly less than c, so r is strictly positive, but it's also going to be less than less than k, sorry. So 0 is less than r is less than k, like so. So we can write c in this form here, and what we're going to do is just plug this guy here into this thing here. So on the left hand side, we're going to get c squared over b, which of course now turns into b squared k squared plus 2bkr plus r squared all over b, and then the ceiling of that. Well, of course, inside we can divide through the b in some of the terms, so we get a b times k squared plus 2kr plus r squared over b, and then we're taking the ceiling of that. But notice that this first part here, bk squared plus 2kr, that's certainly a positive integer, so we can kind of take it out of the ceiling. So let's just take it out like so, and we get this thing here. So we had b times k squared plus 2kr plus this thing here, which may not be an integer, so the ceiling of r squared over b. So that's our left hand side, and our right hand side now, k times c plus k. Well, just plug in what we have for c. We get k times bk plus r, bk plus r plus k, like so. So this is just k squared plus bk squared plus rk. Okay, and if we collect like terms, or notice that this bk squared here is similar to this bk squared, so we can cancel that. And this 2kr, well, we can get rid of one and get rid of this kr from here, so we get kr plus r squared over b equals k squared. Rearranging this gives us r squared over b is equal to k squared minus kr, like so. But remember that r is strictly less than k. So what we're going to do now is define k prime, oopsie daisy, to just be equal to k minus r, which we know is bigger than or equal to 1, because it's an integer and it's positive because of this guy here. And then if we just put that in here, we see that this thing here, well, we can write this as k times k minus r. So that, of course, is just the same as this k minus r is just k prime. And then this k here is just k prime plus r. So now we have the ceiling of r squared over b is equal to k prime times k prime plus r. And now if you have a look at it, it looks very similar to what we have up here, except now our r, or what we had before was a c, and here we've got an r, and what we had before was a k, and now we've got k prime. But remember, what we did is to we knew that we wanted to arrive at a contradiction, and we did that by choosing k to be as small as possible. But I've shown now that there's actually one with a smaller k, because look, k prime, this new k prime here, is k minus r, which we know is strictly less than k because r is strictly positive. So we have k, a new sort of k, which is strictly less than the k we had before, but that's a contradiction because we chose k to be minimal. So that means that there are no solutions to our initial problem. So the a squared plus the ceiling of 2a squared all over b, that can never be a perfect square by this argument here. I hope that has all made sense, and I hope you have enjoyed this number theory problem. I do like these sorts of ones where you kind of have to bound things and then plug them back into themselves and kind of, reiterate your argument ever so slightly. But yeah, I have enjoyed this, and I hope you have too. Thank you for watching. I'll catch you in the next one. Have a great day.